Okay, so this is it, chapter 13, section 3, and we are doing independent and dependent events. So warm it up and come back and check your answer. You are 11, 12. So, okay. So this one, the key was wrong, and we agree that it should be 7/12. All right. So today we're going to determine whether events are independent or dependent, and we talked about that if you were here yesterday. And then we'll find the probability of independent and dependent events. So here is the vocab. And events are what if the occurrence of one event does not affect the probability of the other? Independent. If you're independent, you stand alone. You stand alone. You stand on your own. So an example of independent events that I mentioned yesterday would be like spinning a spinner and flipping a coin. Just because you get heads doesn't mean you're guaranteed some number or some color or whatever on the spinner. They're independent events. But you can use the same experimental piece. You can use a coin, like it says here. If a coin is tossed twice, it's each time you toss it, aren't they independent? If you toss it once and get heads, does that mean you're more likely to get tails the next time? No, it's the same probability each time you toss it. So they are still independent events. If a coin is tossed twice, it's landing heads up on the first toss and landing heads up on the second toss are independent events. The outcome of one does not affect the probability of the other. So to find the probability of tossing heads twice, we multiply the individual probabilities, which we've already used in this chapter, right? 1/2 times 1/2, or 1/4 of the time. So here it is as a rule. Probability of independent events, A and B happening, can be shown. Can you finish the rule? It would be the probability of A, what did we just say?
Times B.
Times the probability of B, right. You're multiplying the two together. Okay, a 6-sided cube is labeled with one. Look at what it's labeled with. Not your classic 6-sided die, right? This has 1, 2, 2, and 3, 3, 3. And then 4 sides are colored red. 4 of them are red. 1 is white and 1 is yellow. So let's find the probability of tossing 2, then 2. So if I just take the die and roll it, what is the probability of tossing a 2?
1/6.
2 out of the 6, or 1/3, right? 1/3. And then what would the probability be of rolling a second 2? Same thing. So when we bring it together, what is your probability?
1/9.
Good. So 1/9. We're multiplying those two probabilities. I guess the colors had nothing to do with the question. That was just getting in our way. Okay. Unnecessary information. Okay, so how about this? If the occurrence of one event affects the probability of the other, these are dependent events. For example, suppose there are 2 lemons and 1 lime in a bag. If you pull out 2 pieces of fruit, the probabilities change depending on the outcome of the first piece that you draw out, right? And here's an image of that. So this shows the probabilities for choosing 2 pieces of fruit. What are the combos, right? Containing 2 lemons and 1 lime. So you could put your hand in and pull out a lemon. Actually, there were 2 lemons in there, right? So the probability was 2 out of 3, or 67%. And the other, there's only 1 lime, so 1/3 of the time. So if you pull a lime out, look what happens. Is it possible for you to pull another lime out? No, because we said there was only 1 lime and 2 lemons. So if you pull out this, if you pull out a lime, the probability that you'll pull a second one is 0, right? 0 out of the 2 now. 0 out of the 2 rather than 3. There's only 2 pieces of fruit after we pull the first out and keep it out. But if we look up here at pulling out a lemon, which was, the probability was 2/3, right? Now the next option would be either a lemon or a lime, so it's 50-50, right? That you'll get the lemon or the lime. So it changes after the first outcome. So the probability of this event, when we bring it all together, is 2/3. The question was, what is the probability of, what was the question? If you pull out, the probabilities change. Okay, so the probability of drawing out 2 lemons, they're asking here, would be, well, the first time you reach your hand in, the probability is 2 out of 3. So you pull it out. And then you say now, you imagine that you had the favorable outcome. So what is left, what is the possible favorable outcome left? 1 out of 2, because the first one you did get a lemon, okay? And when you multiply those together, you end up with 1/3. We're going to practice these in a moment. So let's put this in a rule box. So to find the probability of dependent events, you can use conditional probability. Conditional. So you might have thought it was dependent, but it's really, the second draw is dependent on the first, so it's based on what was the condition after having drawn out the first, right? And here's how you can write that. Probability of B given the condition of A, right? Given that the event A has occurred. So these are 2 events happening, but one is dependent upon, B is dependent upon what happened in your A draw. Okay, so that's how we write it. The probability of event B given the probability of A. So if A and B are dependent, then what are we going to see with, first of all, we're going to see the probability of A, right? And now the probability of B is different than it would have been had we not had A, right? So we do the probability of B based on what happened with A. Okay? So 2 numbers are rolled, 1 white and 1 yellow. Oh, this goes back to that description, I guess. Explain why the events are dependent. Then find the indicated probability. Okay, so if the white cube shows a 6.
I didn't have a 6 on it.
Let me see. Okay, so we said that these are just standard dice. And let's say the first one you roll, the probability of just getting a single number 6 is 1 in 6, right? And then we now say on the second die that's rolled, how many outcomes could we add to 6, given that we actually got 6, right? Would give us a sum greater than 9, and that would be numbers 4, 5, and 6, right? So there's 3 out of 6 that would be in favor, and 3 6 equals 1/2. So we have a probability of 1/6, and then if we get that, we could multiply it by the probability of 1/2, and that can give us this dependent situation, right? So here we have the 1/2, and so do they finish it here? The probability of A and B is multiplying these 2 probabilities together, and we end up with 1/12. So 1/6, and then if we actually get that one, we would have to get 1 out of 2 favorable outcomes, combined total of 1/12. So let's try it again. 2 number cubes are rolled, 1 white and 1 yellow. We're again talking about standard dice, so they have 1 through 6. Explain why the events are dependent, then find the indicated probability. So the yellow cube shows an even number, and the sum is 5. So are these events dependent or independent? I mean, when you roll the first one, we're talking about rolling an even number. Okay, so is that an independent event or dependent?
It's dependent.
That's just independent, right? You're just rolling a die, right? And when you roll the second die, if I got an even number on the first one, like let's say I got a 2, would the sum, would what I roll in the second die depend on what I got in the first?
Yeah.
It would. So these are dependent events, right? So then it's kind of interesting because it would have to be a 2 or a 4, like you're saying, Andrew, because what if we got an even 6? Could we get a negative on a die? You could have 2 plus 3, or you could have 4 plus 1, but what if you had 6? Okay, but look at the statement said the probability of an even number, so let's see if they take that into account. Well, now you're saying, okay, wait, you're saying if we got a 6, we can't have a sum of 5 on our second roll. And
Yeah.
I agree with that. But if the two events are, what is the probability you will roll an even and the sum is 5? So the probability of an even, we agreed, was half. Half of the
Yeah, I thought it was a third.
half of the possible outcomes are in favor of an even. But let's see, what is the probability of, or how many outcomes could then give us a sum?
2.
2 out of 18, right? And so I guess we could make a big diagram showing all of these possible outcomes, but it would require you putting a 1 through 6 for the first die and 1 through 6 for the second, right? And you're looking for all the possible
Wait, why
even
so?
first.
Because 6. You can't roll a negative one.
No, you can't roll a negative one. So if we have the first roll of the die here, 1 through 6, we see that we have 18 possible even first rolls. But when we look deeper into it with the second roll, there are only 2 of those that will give us a sum of 5. So 2 out of 18 is 1/9. Okay? So the probability of an even and a sum of 5 is 1 out of 18.
Well, maybe they did.
And so this is the entire group, isn't it?
Yeah.
It's 2 out of 36. That's what I was just thinking. Really, this is 2 out of a total of 36 possible total outcomes you could get, right? Which is 1/18. So this is simply that 2 out of 18 or 1/9 is the number of possible given just the even first roll. But really for the total probability, we have to say the first probability is 1/2 and the second probability was 1/9. And when we multiply those two together, it's 1 out of 18. And we can see that it's 2 out of the total 36, which is 1 out of 18. Okay, so we do include all of the probabilities in the first roll, even though the 6s aren't useful to us. Okay, interesting. So conditional probability often applies when data fall into categories. So this is just a real world example of conditional probability. This table shows domestic migration. That means people moving around in the country, within a country, not outside of a country. Domestic is within a country. From 1995 to 2000. A person is randomly selected, and so find each probability. So how would you find, well, let's find a more specific question, that an immigrant is from the West? Do you know what the difference between immigrant and emigrant?
Immigrant is the.
Immigrants coming in, immigrants going out.
Good. Kara's saying it. Immigrant is entering, like entering the Northeast, 1537. Coming, entering the West, 2,666 in thousands, so we would add 3 zeros to that. So it's 2 million, 2 2/3 million here. Emigrants is leaving an area, okay? So leaving versus arriving to. So what is the probability that someone is from the West? Whoa. You have to add it all up to get some sort of a total, right?
2654 over whatever that sum is.
Okay, so let's just see if they can give us the total, right? And that's, we see 2,654, because those are the ones leaving, emigrating, out of, they're telling us a total of this, okay, 11,656. And again, does this total here include every single number in this chart? Or just the right side? Find that an immigrant is from the West. So out of all of the total immigrants, right? And what do you think that is approximately? This rounds to 3,000, this rounds to 12,000, right? So it's like 1/4, or yeah, 23%. Okay, let's look at what the probability is that someone selected from the South region is an immigrant. Huh?
No, it's not, because it rounds up to
23.
to 23.
0.28.
Yeah.
0.228, 23. The 2 rounds up. if you're going to the hundreds place.
It has to be 20.
What was this? Someone from the South region is an immigrant. From the South region, how are you going to find that?
3243 over 8 to 85.
And so how are you getting that number?
Wait, immigrant.
8 to 85, right?
An immigrant. This person is now an immigrant. Whoops. So someone selected from the South as an immigrant, so we see the 5,042.
Over 8 to 85.
And you're getting that with, how did you get that number? You're adding these two, right? Immigrants and immigrants. So as you're looking at those from the South, you're adding them, and what do you get? Andrew, did you get it?
Yeah.
Thought you were doing it. What'd you get? Did you get 60%? 61%? Okay. What is the probability that someone selected is an immigrant and is from the Midwest? So just somebody randomly selected is an immigrant and from the Midwest.
And immigrant.
Immigrant.
Add it all together.
That's
That's the
two, yeah.
denominator. Numerator is
And then the numerator is,
280.
did they say Midwest?
290.
2951. So we have 2961. How did that become a 61? It was a 51 here. It should be 51 over the total. Wait a minute. Use the immigrants column of the 11,656 immigrants to, so there, that someone selected is an immigrant. I thought that they were talking about the total.
It's always wrong.
So they're now saying out of all the immigrants, okay, rather than the total. If they say just a random person out of that whole table, they actually have not included everybody here. So I don't like their answer. I think it should be out of the total. Although if we take this, we could, if they told us this, we could find it, right? But given this, what is the probability that someone is an immigrant? That's basically saying you could be an immigrant or an immigrant, right? So, And finally, what is this last one? An immigrant and Midwest? They're going to combine what they just found, right?
Wait, so is this one is the whole?
The first one should be just the Midwest, not just the immigrant Midwest. So you would add them both together.
Okay, so they're using what they said was the probability of you being in the immigrant population from the Midwest, which is not really how we think that's phrased up here, but that's here. And then they say, what's the probability of being an immigrant at all out of the whole total? And when we multiply those together, it's a very small percent who are both from the Midwest and immigrants, 12.7. Okay. So when we're talking dependent events, the theme is that when you remove something, or let's say you remove a lime from the bag and you don't put it back, the next event is dependent on the first. But in many cases, events are independent when you put something back. In other words, if we had that bag of lemons and limes, right? Lemons and one lime. If we pull out one lemon and then we put it back and we go and we pull out again, we're dealing with the same probability each time. And we could just simply multiply the probabilities like we talked about with the independent events earlier. You all know this? What the suits are like in a deck of cards? You have 13 cards and, okay. So if 2 cards are drawn from a deck of 52, would those together be dependent or independent events?
Dependent.
They would be what?
Dependent.
Dependent, right? So if I pull a card, any card like Ace of Hearts, and I keep it out, I'm pulling a second card. The second choice now depends on what I pulled out, right? Okay, so what is the probability of selecting 2 hearts when the first card is replaced? What's the probability of selecting a heart at all? 1/4. And so if we replace it, what's the probability of 2 hearts?
1/16.
1/4 times 1/4, right? Which is 1/16. Good. What is the probability of selecting 2 hearts when the first card is not replaced? Not that, but, okay, so since we're not replacing the card, then the probability of getting 2 hearts now is the first probability, 1/4 of the time, and then the probability of getting a heart after a first card was a heart. Okay, so we say we have 13 out of 52, or 1/4, multiplied by 12 out of 51. And you end up with 1/17. And then a king is drawn. So the probability that a queen is drawn and not replaced, and then a king is drawn. So the first one is 4 out of 52, and the second is 4 out of 51, right? Because we didn't replace it. So then we can reduce it down or whatever, and we should have, ooh, look at that. 4 out of 663. But then there are fewer kings than there are like hearts, like we saw back here. There's a lot of hearts, right? 13 hearts.
So every 663 times you've got a king and a queen.
4 out of every 663 times you will draw out a queen and then a king. And would that be the same probability for a king and a queen? Yes. Any 2 cards. Any 2 cards. That's your probability that you draw them in that order. Actually, as long as you're not taking into account suit, right? Because then it probably drops to 1. Well, what would it be? I mean,
More?
let me turn this. Try this and come back and check your brain.
So I must have done it wrong.
I don't know how that happened, but here we have these answers. And try these, and then you're on your way. And this is your lesson. And